Look at this ox-drawn well from a 1960s Deccan village. For generations, Indian agriculture has operated through intense manual labor and a total reliance on the unpredictable timing of the annual monsoon. When those seasonal rains fail, the result is devastating. Extended dry periods, frequently driven by severe El Niño patterns, drain the soil's moisture until the earth itself begins to fracture. To compensate for dry spells, farmers historically turned to flood irrigation. You can see the massive volume of excess water pooling in these trenches. This is an open-loop system. Resources are applied to the field based on a schedule, with no real-time data from the soil to signal when the crops are actually saturated. Pumping water based on a predetermined routine or intuition often leads to either drowning or dehydration. Against the extremes of modern climate patterns, this lack of feedback guarantees resource depletion and eventual crop failure. Water scarcity is only the first threat. Down at the microscopic level, fungal spores can attach to a healthy plant and begin rapidly multiplying across the surface of the cell wall. Under specific temperature and humidity zones, this infection manifests as wheat rust. These reddish-brown pustules physically rupture the leaf's surface, destroying the plant's ability to photosynthesize. In different microclimates, powdery mildew takes over. This fuzzy white coating blankets the leaf, suffocating vital structures and preventing the plant from reaching maturity. The traditional defense against these threats is visual inspection, but by the time a farmer can spot discoloration or lesions with the naked eye, the pathogen has already compromised the internal tissue and locked in a reduction in yield. Human detection is simply too slow for rapid-onset biological threats. By the time the damage is obvious, the economic devastation is already complete. Companies like AgriPulse Technologies are addressing these vulnerabilities by shifting towards precision agriculture. Their Smart Crop Guardian replaces guesswork with a closed-loop system. It creates a continuous feedback cycle that adjusts resource application based on the constant stream of data coming directly from the field. By translating the physical realities of the farm into digital data points, the system allows the crops to be sustained autonomously, even during sudden environmental shocks. The architecture relies on the Wireless Sensor Network, or WSN, shown in the bottom left quadrant, which divides the farm into digitally monitored sectors. Each sector's microcontroller unit pulls in localized, high-resolution readings on soil moisture and pH balance. This granular data travels over an MQTT protocol, a secure digital route that sends every measurement to a central master microcontroller. The master node processes this stream using predictive analytics. It calculates the exact volume of water each sector requires and determines the precise second it should be delivered. Digital logic then triggers physical action. The master MCU operates a network of flow sensors and electronic solenoid valves, snapping them open to deliver the calculated dose of water and shutting them the moment the soil target is reached. To maintain power efficiency, the slave nodes remain in a deep sleep mode until the master MCU periodically awakens them for the next round of data collection. This interconnected hardware creates an autonomous system where hydration is delivered only when sensors confirm it's needed, ending the reliance on wasteful flood irrigation. This data is managed through a clean, localized interface, distilling complex sensor outputs into a dashboard the farmer can access directly on their smartphone. The mobile interface also functions as a diagnostic tool. Here, the farmer uses the camera to scan a rice stalk, initiating an image-based disease analysis. A convolutional neural network breaks the photo into a pixel grid, comparing geometric patterns and color data against a cloud-based library of pathogens until a match locks in. Once identified, the system instantly generates a targeted recommendation for treatment, allowing for a localized intervention before the infection can spread. Putting this level of diagnostic power in the farmer's pocket collapses the response time, neutralizing biological threats that would otherwise go unnoticed. These IoT and AI tools expand a farmer's capabilities, providing a level of oversight across hundreds of acres that was once physically impossible. The result is a measurable reduction in resource waste. Pinpoint watering conserves vital groundwater, while early detection prevents the need for the blanket application of chemical pesticides. This optimized reality stands in contrast to the traditional model of guessing against the climate. The struggle to react to sudden drought or disease is replaced by a managed, data-driven process. The smart crop guardian shifts farming from an unpredictable gamble into a precise, predictable science. As climate patterns become increasingly erratic, adopting these closed-loop cognitive systems provides a working model for maintaining stable food production and agricultural income.